We are recording. This is March 18th, Wednesday, and we're doing sample problem 5C together from your book on page 175. So we have a sled, it's on ice, somebody gives it a kick, it starts to move. You can all visualize this. And at some point it will come to a stop. The force that will stop it is kinetic friction. So we have its mass, we have its initial velocity, 2.2 meters per second squared. We said yesterday its final velocity, because we're looking for the point at which it stops, is 0. That makes life easy. And we're given mu k, the coefficient of friction between the sled and the ice. Okay, we have two equations that we can work with here, because we're working on work kinetic energy theorem. So we have work equals force times distance, or we could say that this is delta x. And that's a more familiar and comfortable term for many of you. We also know that work is equal to the change in kinetic energy, which means that work is equal to 1/2 final velocity squared minus, or 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. And I know that's a little crowded, sorry. We'll move mu k over. Okay, we know that final velocity is 0, so that whole thing goes away. Great. So we have work is equal to, equal to 1/2 mass velocity initial squared, negative 1/2 mass initial velocity squared. There, negative. Okay. Where do we go from here? This is what we're looking for. So we're going to end up plugging everything back into that equation to solve for delta x. One approach, and this is not the way your book does it, but I think it's more intuitive and makes more sense, is to solve this for delta x to begin with. So work divided by force equals delta x. Okay. So at this point we know that we're going to have to build expressions for both work and for force. Well, work is done. So now we're up to this, negative 1/2 mvi squared over force equals delta x, which would be fantastic if we knew what? Force. Can we build an expression for, and this of course would be net force, for the net force on this thing, on the axis of the motion? Well, there's only one force acting on this on the x-axis. Force of friction. Because when you push it, once your foot's no longer in contact, you're no longer exerting a force. So there's no other force on the x-axis. So the entire net force is actually the force of kinetic friction. Do we have the force of kinetic friction? Can we create an expression for the force of kinetic friction? You betcha! So mu k equals fk over fn. We can create an expression. We have mu k, and we can figure out a way to get to mu n. Mu k fn equals, what did I say? Mu n. Oops, okay. We can figure out a way to get to, and then I just put in normal force twice. We'll try that. Okay, so great. We've got this. How do we get to that? The words you love to hear, sum of forces. Just a brief one. This is a relatively painless sum of forces. Well, yeah. Sum of forces y is 0, and it's fg plus fn. Pretty easy. Negative fg equals fn. Okay, so that means negative mass gravity equals Fn. So now if we plug this into that, and this into that, we got ourselves a party. After doing some cleanup here, we're showing this and then showing the substitution for this. Now we're going to put this whole thing under here, times negative mg, and that whole thing. Yeah, I guess in theory you could.
Should we not?
I didn't even notice that. Yeah, you could. Algebraically, you could do that. And as has been pointed out, we can do that. So then we end up with negative 1/2 vi squared over mu k g, well, negative 1. So the negatives cancel, yeah, equals delta x. Okay, let's plug in some numbers and have some real fun. Well, that's what we just, so the discussion was just this. Let's see. If we didn't cancel out these negatives, let's look real quickly at that. So let's put some numbers in. Well, you know what? If we go ahead and use a negative 9.81 meters per second squared, we end up with a negative distance. So it depends on, note that the velocity and the force are in different directions. So we would be calling one of those a negative. So we can either call...
Well, I was just thinking, like, whenever it's negative mg, you know how you taught us to, like, put it...
Okay, so we've got our numbers plugged in. We're going to have a detailed discussion about sine momentarily, but for right now we're just going to deal with this. And we'll get a negative distance because our distance is operating opposite of our force, which we allowed to be a positive. So for a raw number, we get negative 2.466487504 for delta x. And the book sig figs are, as usual, wrong. They claim it's 2.4. We say, no, it's 2.5. So we know that the magnitude of the displacement is 2.5 meters. And then we can add a direction in lieu of sine. That makes sense? That work? We're going to have a detailed discussion about sine. You are assigned numbers 1 through 5 on 176. Number 5 has got multiple parts. It's a little bit of a booger. So I'll give you time to work. So in thinking about sine in more detailed terms, we have that initial velocity and that displacement operating in one direction. We have the force of friction acting in the other direction. So if we're being honest, this force of friction, and I'm going to make up numbers here, if this was 520 newtons, it should be negative 520 newtons. And we would assign it that negative sign based on the fact that it's in the opposite direction of the motion. You know, if we had another force acting in a positive direction, we would assign that a positive. So these are just, the signs here indicate that this is in opposition to the direction of travel. So if we do that, we know that this has to be a negative number overall. And then we can go down to, so we didn't do that, yes. We forgot to do that.
So even at the end you can't do that?
You could, yeah. There would be a way to add that, to sort of Jimmy rig it and add it at the end if you wanted to. That,
So then you would have got a positive?
yes, then I would have got a positive displacement. I chose not to, just to get through the numbers for people, because I thought it was a limited number of folks who really wanted to examine the sign issue. Okay, so if we look at this, we have Fg plus Fn, so negative Fg equals Fn, it's the worst F I've ever written, so negative mass gravity equals Fn. Well, that makes perfect sense, because, normal force is up, the negative of mg, which is going to be negative 9.81 times the mass, would be down. So this gives us a positive number for Fn. Perfectly logical. But we're putting this back into an expression for Fk, and we know that the number for Fk has to be negative. So we can kind of finagle that and say, okay, well, we know that this whole expression has to be a negative number. And we could put that in at the end. This is the plus sign that so we had work, which was equal to, negative 1/2 mvi squared, and that was put in here, and over force, which was then mu k times negative mg, or negative mg times mu k, it doesn't matter. So we canceled out the negative signs, the negative 1 in essence, and we canceled out the m's. But that still leaves us with this piece having to overall be a negative number if we're going to, oh, you know what, canceling out the negative signs was our big mistake. We shouldn't have done it. Yeah, we just shouldn't have done it. If we had not done that, and we had left those negative signs, then we could cancel out the m's, that's fine. But then knowing that this should be a negative number overall, we would end up getting a positive displacement. Okay, see you tomorrow, and we'll be working. Maybe I'll see you tomorrow.